So question 1, use L'Hopital's rule to show that Planck's law results in this. The limit as lambda goes to 0, this one f of lambda equals 0. So this one here, limit as this goes to 0, show that this equals to 0. The limit as it goes to infinity, show that it goes to 0. And then yeah, and it also says use L'Hopital's rule, so it's giving us a hint. And so this law models black-body radiation better than Rayleigh-Jeans Law for short wavelengths. Alright, so recall, let's go to solution. So recall L'Hopital's rule from my earlier video, and the earlier video shows that basically, suppose f and g are differentiable, and g prime of x is not equal to 0 on an open interval I that contains a except possibly at a. Suppose that, where we have the limit as x approaches a of fx, so if you have this one of fx going to 0, and then you also have limit as g of x is limit of g of x goes to 0 as x approaches a, or you have it going to plus or minus infinity, and the other one is also plus or minus infinity. In other words, we have an indeterminate form of the type 0 over 0 or infinity over infinity. Then L'Hopital's rule says, well, then the limit as x approaches a of f of x divided by g of x equals to, well, the derivatives, the limit of the derivatives. So you can just take the derivative of f prime of x divided by g prime of x. And this is a scenario where g prime of x's derivative is not equal to 0 on an open interval that you're looking at, except possibly at a, except at, yeah, because again, when you're doing limits, you're not actually plugging in a, so you're approaching that value. So yes, except possibly, but again, it depends on the function, it depends on the scenario. And if the limit on the right side exists, or is infinity or negative infinity. So basically, if this is indeterminate, because you have a 0 over 0 or infinity to infinity, essentially it's saying which side is going to infinity or 0 faster, the top or the bottom. And if it's the top one going to infinity faster, then that means it's going to 0 overall. If the top, if the bottom is going to 0, going to infinity faster, then it's divided by infinity. It's going to go to 0. But if the top one goes to infinity faster, it's going to go to infinity. Yeah, so basically if the bottom is faster, it goes to 0. If the top is faster, it goes to infinity. Anyways, going further. So let's take a look at the following limits while grouping the constants together to simplify the equation. Alright, so let's just write our function down. F of lambda equals 2. Let's see what we have here. Again, this is going to be 8 pi hc and then lambda to the power of negative 5. So let's write this one down. 8 pi hc lambda negative 5. And then we're going to divide this by, then what was the bottom? Bottom is e to the hc divided by lambda kt and then minus 1. So e to the hc divided by lambda kt, then all minus 1. Alright, so now that we have this, and we're going to group the constants together just to simplify it. I'm going to move this lower. Move this over here. I'm going to call this part right here, this 8 pi hc, so this part right here, I'm going to call this as a. Yeah, so better you have to put it in this kind of bracket. So this is going to be a. A is 8 pi, let's put a equals to 8 pi hc. And then, so we have that. Well, I'm also going to take this and move it over here. This is going to be, we'll call this b. B equals to, well, just this part here. So hc over lambda k, like that. Just so that we have, actually no, we can't put the k there. That's not a constant. I mean the k. I mean the lambda. We can't put the lambda there. We have to put the k. The lambda is a variable. That's this one. So we put this like that. B equals to hc over k, just to simplify. Otherwise, we're going to be writing a bunch of constants. So this equals to, this is going to be a lambda to the power of negative 5 divided by e to the b. So this hc divided by this k is going to be, this is going to be b divided by kt. So it's going to be divided by, divided by lambda t. I always get confused, lambda and k and t, like that. I'll just put that bracket around it and move it, and put a minus 1 over there. So that's what we have. Alright, so now we can take the limit. So limit, let's do the the first one. So limit as lambda approaches 0 from the right side, or plus of f of lambda. This equals to limit as lambda approaches 0 from the right side, or the plus. And we're going to put this over there. So a lambda to -5 divided by, divide this by e to the b, and then divided by lambda t minus 1. Like that. Yeah, so now what happens here as this goes to 0, so this part, this lambda 1 is going to be, well, a 1 over 0, because it's power of -5. That goes to infinity. Now this part over here, we're going to have, this scenario is going to be, well, this is going to be, I'll put the whole thing actually. This is going to be e to the, well, this is going to be b divided by 0. So I'll just put it 1 over 0. That's how it's going to look like. Minus 1. This is the same thing as, well, this is 1 to the 0. This is going to infinity. So that's going to go infinity. Yeah, e to the infinity. E to the infinity minus 1. That's just infinity. So e to the infinity minus 1 is just going to go to infinity. In other words, we're going to have a scenario of that's indeterminate. So we can apply L'Hopital's rule. Infinity over infinity. Alright, so let's just box this out. So that means we could apply L'Hopital's rule. But before we get to that, let's just do the other one as well. So and, so this one, and let's just do the limit as lambda goes to infinity. Lambda goes to infinity of f of lambda equals to, let's just write this for completeness. We're going to write that exact same thing. That's going to be it's going to be 0 over 0, just by it's because it's the same equation, but instead of infinity we're going to instead of 0 we're going to infinity. So power -5, and this is going to be e to the b divided by lambda t minus 1. All right, so now when you plug in, this is not 0, this is infinity. When you plug in infinity in this one, you're going to have a 1 over infinity for the lambda, and then this is going to go to 0. And this part right here, you're going to have a e to the, well, 1 over this infinity, that's infinity there, minus 1. This is going to go to e to the 0 minus 1, which goes to, well, e to the 0s is 1, so 1 minus 1, which equals 0. So 1 minus 1 goes to, so you're approaching 0. So this goes to a 0 over 0, and also an indeterminate as per L'Hopital's rule. So we have both 0 over 0 and infinity over infinity, like that. Alright, so yes, in both cases, we could use L'Hopital's rule. So let's go further. So let's do the limit at infinity first, just because it turns out to be the easier. This one you have to do it multiple times for the L'Hopital's rule. So let's do this one right now first. The limit as lambda goes to infinity of f of lambda equals 2, and so we're going to look at this over here, but instead of writing equals to, I'm going to put the L'Hopital's rule. You could use this notation, equals to with an h on top, so we're going to do L'Hopital's law on it, and this equals to limit as lambda goes to infinity of now the derivative on the top and bottom, d over d lambda of this top part, which is our a lambda -5, like that. Alright, and then we're going to divide this out by the derivative of this denominator there. So derivative d over d lambda of this in bracket, close bracket, so e to the b slash lambda t, put it like that, like this, then minus 1. Alright, so now let's do the derivative. So on the top one, we know that this equals to, well, let's put this on, this equals to, let's put it over here, equals to limit as lambda approaches infinity. So lambda approaches infinity of, well, a, and then we're using our power law, this -5 goes down. So this can be negative, so -5 goes down. and we're going to have then we subtract the power, 6. So negative 1 on the top is going to be negative 6 like that. And let's just move this in the center. And then this is going to be like that, divided by, now this one, well, this is negative 1, the derivative of that is just going to go to 0. So we can just leave that out. So now this, all we need to care about is this one here. So e to the b, so this is the exponential function, the derivative is itself, but you have to apply chain rule. The derivative is itself, e to the b divided by kt, like that. And then we multiply this by, again, chain rule. So now we take the derivative of this inside, so b over lambda t. Yeah, now we have to use chain rule, so the derivative of this top part inside, well, that's just going to be, let's just write this over here for completeness, d over lambda of, I'm going to move this like this, b times lambda t to the negative, this is to the negative 1. So that means we're going to bring down a negative 1. And then it's going to be negative b over, and then we're going to subtract by a power. So that's going to be a 2 there. So then we're going to put this like this. This is just a bubble to see how we're calculating it out. Yeah, just put it over there. And then this is going to be negative 1. And when you subtract it, when you do the power law, so you move this negative 1, then it's going to be negative 2. So negative 2 or just divided by like that. Lambda t to the power of 2, like that. And then we have to do chain rule again, which is the inside, so multiplied this. So this part right here is this. Then we have to multiply it by, just for a refresher. Okay, so this is going to be now chain rule is the inside one. It's going to be d over d lambda of this inside function, so lambda t. Like that. And that derivative is just, well, t times by t. And I'll just move this over here. That's just over there. I'll just leave it like that. Put it all inside. So this t like that. That's this one, and then this one is over there. Yeah. Let's do a better bracket. Okay. Alright, so now let's move all the constants out of this limit using limit law. So we could move this negative 5a out of there. So we're going to have a negative 5a, just to simplify it further. Now we can remove all this stuff. So we can remove this negative b. Yeah, this negative b at the bottom. But also notice what we'll have there. This is, so we have this divided by lambda t squared. But also we have to have this t over there. So just take that another constant. The t over there. Yeah, but so that t goes at the bottom, but this one's divided by t squared and lambda squared. So that means this has to flip on the other side. So then we're going to have a t squared on the top. T squared like that. And then this lambda is going to be on the top squared. And we're going to get to that soon. Just going to be times it by limit as lambda approaches infinity of, now we're going to have this, yeah, so this divided by, so we have this this number divided by this divided by lambda t squared. So then again, those just flip on the top. So we're going to have a lambda squared times it by lambda to negative 6. And then we're dividing this all out by what's remainder is just this part here. Yeah, that's actually the only thing that's remaining. E to the b lambda t. Alright, so now let's do some cancellations and simplification. So this plus, this negatives become a plus. This t squared cancels with this. So what we're left with now is this equals to, and also this combines with this one here. So this becomes a negative 4. This is going to be a 5a over b limit as lambda approaches infinity of, now we're going to have a lambda to the negative 4 over e to the b lambda t. Yeah, and also forgot to add a t there. So there's a t over there. Alright, so now we're going to evaluate our limit, and let's plug in the infinity over here. So the top part is going to be a, well, 1 over a infinity goes to 0. And then this bottom one over here, this is approaching, let's see, let's put an arrow. So this is approaching e to the 1 over infinity, which is approaching e to the 0, which is approaching 1. So e to the 0, or any number to the power of 0, is yet defined as 1. So in other words, this equals to 0 over 1, which equals to 0. Like that. So there we've solved the first one, or one of the conditions of the problem, was show that this goes to 0 as the wavelength goes to infinity. The next one is to show that as wavelength goes to 0, that the function also goes to 0, as opposed to this one's to infinity. So now let's keep going further. Alright, so now if we look at the limit at 0, so the limit at lambda is approaching 0 from the right or positive side, requires several iterations of the L'Hopital's rule. So if we were to take the limit, so we're going to look at this case here, but again, it's the same function, we're just changing the limit. So we're going to go, so we'll start off where we ended off over here. So we're going to go limit as lambda approaches 0 plus, from the right side, of f of lambda. This equals to, well, we'll put the h in there, and start off where we left off here. So this is going to be 5a t over b times it by a limit. Instead of infinity, we go to limit to 0 plus. And this is going to be of lambda to the negative 4 divided by e to the b lambda t. Alright, so now when you plug in 0, what we get on the top is, well, we have a 1 over 0 that goes to infinity. The bottom is going to be, well, a e to the 1 over 0, which goes to, well, 1 over... This is going to be e to the infinity. So 1 over 0 is going to go into infinity. This goes to infinity. So in other words, this equals to an infinity over an infinity, which is not good news. Alright, so this is still indeterminate, but note that each time we use L'Hopital's rule, we gain a factor of lambda in the numerator, as well as a constant factor, and the denominator is unchanged. And we could see this right here, so we could keep going using the L'Hopital's rule. So let's just write this down. Limit as lambda approaches 0 from the right side of f of lambda. This is going to be equals to with the h, so L'Hopital's equals to. And we're going to start off where we ended up on this one. So put the h on top there. This is going to be 5a capital T over b. And then this is going to be limit. Yeah, limit of this one. Let's just solve the full derivative. So this one, take the derivative of that. This is going to be limit as lambda goes to 0 plus 0 from the right side. This is going to be lambda to the negative 4. The derivative of that is going to be, well, negative 4 times it by lambda to the negative 5. Then divide by the bottom is going to be, well, using the same exponential rule for a derivative, and then chain rule multiple times. We're going to get a e to the b lambda t times it by chain rule. Chain rule means we're going to have at the bottom is going to be a negative b. This is yes, this is power of so this is divided by lambda t, or in other words, multiplied by lambda t to the power of negative 1, and then it's going to be a lambda t squared. This square bracket like that, and then times it by, again, chain rule inside. This is going to be t. This will be exactly the same thing over here. So this is going to be negative b. Because this denominator is the same thing, so we're going to get the exact same one each time. So negative b divided by lambda t squared, and then times by t. That's exactly what we have here. Then we take out the constants again, or just simplify it. So we can have, there's a negative here. Let's just cancel all the negatives. Negatives cancel. Negatives cancel. We're going to have this 5 times 4 is 20. There's a t there. T cancels. T over there cancels. And this t squared goes on the top. This lambda squared goes on the top. So this equals to, let's write this down as 4 times 5 is 20. divided by 40 times by, this is going to be AT squared. So this T squared goes over there. So you're dividing by and then dividing by again. So that just flips, goes over there. And then this B is just by itself, like that. And this is going to be times by a limit as lambda goes to 0 plus. And this lambda squared is going to go on top, like that. And then also, I forgot that there's a B there, and there's a B here, so that's going to be B squared, like that. And then we're going to have now, this is going to be lambda squared times it by lambda to the power of -5 divided by e to the b, like that, kt. Or we could simplify this further, just save time. This is minus the, so -5 in the power of 2, that just becomes -3. Add those powers together. So this is what we have now. And now this scenario, because we have the exact same thing, so nothing changes in this one. All we have is the constants and change. So this is the exact same as this, except this instead of -4, it's a -3. And that's going to be, it's going to be the same thing. 1 divided by 0 goes to infinity. And the bottom is 1 divided by infinity. I mean, this bottom just goes to infinity. So we have infinity over infinity, but this one is 1 less than this. And it's exactly the same thing. So this equals to, let's put this arrow, infinity over infinity. So it's the exact same thing. Yeah, so it's the exact same thing, except we have a constant and this power goes down. So now we can see a pattern. So if we use the L'Hopital's rule 3 more times, the exponent of lambda in the numerator will become 0. So the next time will be -2, then -1, then it goes to 0. And when it's a 0, well, that's just 1. So then we don't have this infinity on the top. So what we could do is, that is, for some constant ki, just a sequence of these, all constant integer I there, then, and we're going to write this as, this first one's going to be our k1. It's not both ones constant. This is just for this case. So we're going to have, this is going to be k1, like that. And then so then what we're going to have is, well, let's just write this all down, and we can notice the pattern. Limit as lambda goes to 0 plus, or from the right side, of f of lambda, this equals 2, or this L'Hopital's equals 2. And let's write off where we ended up here. So this is going to be k1 times by limit as lambda approaches 0 from the right side. And this is going to be lambda to the power of -3 divided by e to the b kt. Then if we apply L'Hopital's rule again, just following the pattern, this equals to h equals k2. So we're going to have another constant times by the limit as lambda goes to 0 plus, from the right side, this can be lambda to the power of -2. And then the denominator is going to be the exact same thing. Lambda t, like that. Alright, so now I keep going further. So then, yeah, keep following the pattern. We're going to eventually get this one here, lambda, this is equals, h equals, or doing the L'Hopital's rule again, because we're going to keep getting a infinity over infinity until we get further. It's going to be k3, and k3 is going to be limit as lambda approaches 0 plus, this is going to be lambda to the power of -1, so we just need one more. Lambda t, like that. So the next one's going to be equals to h. Use a L'Hopital's rule again. We're going to get another constant, the last one, k4. And k4 gets to limit as lambda approaches 0 plus from the right side. This is going to be lambda 0, like that. Then this is e to the b kt. And lambda to 0 is just equals to 1. And this is going to be, well, this one we already know is infinity. So this is just, we already know this is going to be, move this over. Let's move this over like this. Is going to be e to the 1 over 0, which goes to e to the infinity, which goes to infinity. So in other words, we're going to have a equals to a, we're going to have a scenario of 1 over infinity, which approaches, well, 0. It's equals 0. And yeah, that's 0. That's exactly what the question 1 says. So yeah, so this confirms question 1. So again, there is the limits. So we show that the limits of this function of Planck's law approaches 0 for when lambda goes to 0 or lambda goes to infinity.